So recall how I'm trying to convert a square wave to a sine wave using RC networks. It's the final stage in the DC to AC converter. About that, briefly recall that a low-pass filter is a filter that allows low frequencies to pass, which is how you smooth out a sharp square wave into a smooth sine wave. Your input signal goes through a resistor and a capacitor in series, and this produces your output signal. Your input signal through the filter and your output signal, you take the voltage across the capacitor, the resistor and capacitor in series, but the actual signal only passing through the resistor. And your time constant is the resistance times the capacitance, which is the time it takes for about 60% of the way for the capacitor to change from one voltage value to another. 5 tau, 5 times tau, is about the time it takes to be close enough to 100% from one voltage to another to not worry about it. Now there's two issues with this type of filter. The first is that there's a voltage drop at the end. The output voltage, the magnitude, it basically amplifies negatively, de-amplifies, whatever you want to call it. We've seen that before. I had a video on it. But as we'll see, it's a little more severe in this case than I expected. The other issue is the signal passes through this resistor no matter what. So I want this resistor to be as small as possible, so as much current goes through as possible. And as we can see here, in order to have R smaller to get the tau we need to make C bigger. So I basically use the biggest ceramic capacitor I have because I don't want to use an electrolytic. I don't want to use a polar one just for safety. So I'm using the biggest non-polar ceramic I have. And then that allows me to have, since my frequency is 60 hertz, it's really low, I can have on the order of a couple hundred ohms here. That's pretty good. Something like 333 ohms or thereabouts to get 1/60. So I just put in a 1K potentiometer to try and tune it, but things didn't go quite as expected. Now visually what should happen is we have our square wave input, and after one filter, it should be mostly triangular, a little curvy triangular. After a second filter, it should smooth out and be wobbly-ish. And then if we add a third filter, which I won't because I'm trying to limit how many resistors I have to have, but if we added another, it would get smoother still and be a nice sine wave. That's what's supposed to happen, and it does, but it turns out the losses are just too great. There is a way to solve this that we'll have to get into in the future, but right now let me just show you the problem. So right now, I have my 60 hertz oscillator board plugged into my H-bridge board, and I have as the load a 220 ohm resistor. I'm trying to simulate a low impedance load. This is what's being powered by the H-bridge. Now 220 ohms is still fairly high when you compare it to something like a speaker or a motor, but it's fairly low. Now you'll see one problem immediately. I have two capacitors plugged in, but the potentiometers, the resistors, are at 0. There's no resistance there. The only resistance is the 220 ohm load. And even with that little of a load, you can see it's starting to filter, so that's not terrible. But here's the other thing. Instead of having a load, let me just measure directly. So I'll actually unplug the load, and I'm going to plug the oscilloscope directly into the H-bridge. And I guess technically the oscilloscope is the load. Now we see what we saw before. Here's the wiggle, and you'll see this is the 0.24 and about 4.5 volts. That's where we should be. So the oscilloscope probe is 10 mega ohms. It's a big resistance. But if I put it back how it was, where I have a 220 ohm load, and I am measuring across that load with the oscilloscope probe. So now the oscilloscope probe is having very little effect. You'll see 2 to 4, we've lost voltage. So just the load itself, this filtering action, is already cutting the voltage even with no technical filter. It is a filter because you've got a resistance and a capacitance, so it's filtering, but we've already lost half a volt just from a 220 ohm load. That's pretty severe. But now, let me try and actually filter it. So I'm going to turn up, and I should mention, the capacitors I'm using, the ceramic ones, are 10 microfarad. I didn't think they even made them this big, but I found them. 10 microfarad ceramic capacitors. Those are the biggest ones I could find. So let me begin to turn up just the first potentiometer. and I've barely moved it. This is probably not even 100 ohms. And you can see if I do this, we're down to 2 volts from 4.5, and it's not even a triangle wave yet. This is basically one time constant. If I try to turn it up to get down to a triangle wave, which is what the first one should be producing, look at this. We're running out of voltage immediately. I keep having to increase the wave here, turn up the resistance, and now it's completely destabilizing. If you can see, I'll freeze frame it. We're still not quite triangular. I'm down to a division of 50 millivolts. It's having trouble measuring accurately now. So this is not going to work. If I bring it back up to 2 volts, if I try to do the 2 filters just a tiny bit, even just that much, look at that. Almost at 0 signal, and we've barely smoothed that a bump at all. So having a low impedance load in series with the filters is just demolishing the voltage. Now, let me illustrate something. I will once again take away the 220 ohm load. And as the load, I'm going to have the oscilloscope probes. Here, let me plug it in correctly. So what I did was just remove the resistor, because I had a 220 ohm resistor in parallel with my 10 mega ohm probes. I removed the resistor, so now it's just the 10 mega ohm probes in series. And it's still a bit curvy. There's still filtering going on, but now the potentiometers are currently at 0. So now let me start turning the first one up. And we can see I'm actually getting down close to a triangle wave that I wanted. But the voltage, look at the voltage. So back with them at 0. See, we're above the 4 mark, so 0, 2, 4 and a smidge. So we're very close to the 4.5 because the oscilloscope probes have so much resistance that the other resistance in the system is having very little effect. It's not much of a voltage divider anymore. The oscilloscope probe is taking it all. No, that's not that useful because this would only work as input to a microcontroller or a MOSFET or something like that. But by taking away the load, we did get our voltage mostly back. But to get down to the triangle wave, I barely add any resistance, but there, that's about our triangle wave. So from 4 and a smidgen down to 2. Here's the 0 and 2. I'll increase it so the dividers are 1, so 0, 1, 2. So to get our rough triangle, I go all the way down to 2 volts peak from just over 4. And if I turn up the second potentiometer on the second filter, basically activating the second filter, I can get a smoothish. This is good enough. This is not a sine wave, but it's pretty close to a sine wave. It's close enough for what I want to do. And I have to bring that up just so we can see it. Now, this is half a volt separator, so it's only a 1 volt peak. So we've gone from 4.5 volts to 1 volt. And you say, well, couldn't you just turn up your supply into the H bridge? I can, but it has very little effect because it's limited by the oscillator a little bit. I would have to increase the output of the oscillator as well, and it would just absolutely blow the power consumption of this entire circuit just to get any of this voltage back. But the filter works this way. And you can see if I keep turning up this resistor, we get a little bit of a nicer sine wave. And if I added a third capacitor, a third filter, it would get nicer still. But this voltage clearly just won't do. So there is a solution to this problem. In fact, the two problems we have, the voltage loss and the inferior filtering. The inferior filtering is due to my capacitor choice because I wanted to preserve the current as much as possible, but clearly I'm not going to be able to do that, so I may as well use a better filtering setup and just amplify the end result into whatever current I need. And then there's the voltage loss, which technically, if I'm amplifying, is not a problem because I can just amplify it as much as I need. But every time you lose voltage, there's a chance for more noise to come in, so the signal could get pretty wiggly. So it would be good to re-amplify the signal after each step to minimize the noise introduced. Every step will still introduce noise, but if you drop the voltage and bring it back and then drop the voltage and bring it back again, you're introducing less noise because it's all about the signal-to-noise ratio. If your signal is this tall and your noise is this tall, then it's really hard to separate them. But if your signal is this tall and your noise is this tall, then the noise is not as noticeable. But if you shrink the voltage, shrink the voltage, shrink the voltage, now it's down by your noise, and when you amplify it, here's where the noise was, here's where the voltage was, and you bring the noise up with it. But if you only shrink the voltage and then bring it up, every time you're bringing the noise up a little bit, but you can be careful and not bring it up too much. So I'm putting this project slightly on hold. I'm going to have to get into amplifiers more. We're going to work our way through audio into the operational amplifier. So for now, we're going to dump DC and we're going to get into some audio, some speakers, some microphones, and other types of amplifiers. And while I get that set up, I'll be seeing you.